This is Shelley Physics, Motion of Charges in a Magnetic Field, Part 2 episode. This is probably one of my favorite episodes because we're going to be using FB equals QV cross B on some applications which really intrigue me. Mainly, can we make charges go in certain places? Can we make a flow of charge do what we want it to do? If you're thinking about going into particle physics or something like that, if you ever heard of a particle accelerator, that's the kind of things that these people do. They use magnetic and electric fields to control the flow of moving charge. And that's what we're going to see here today. We're going to look at a device called a velocity selector and a mass selector, or we call it a mass spectrometer if it's used as an instrument. But from our last lesson, we learned how a charge is forced when it's moving within a magnetic field. You see all those parts working there. This is the velocity of the moving charge. That's what the V stands for. We have the magnetic field that it's moving in. We'll call it the applied magnetic field. And this is the force. And keep in mind, it's a magnetic force. What we really haven't covered yet is how a charge produces its own magnetic field as it moves. But because it is producing its own magnetic field, we see the result of a force acting on it from an external magnetic field. Just like a magnet doesn't do anything when it's not around a magnetic field, but you put another magnet near it and it might be attracted or repelled toward that other magnet. So this is a force applied to the moving charge, and that's really important because, as we can see from this expression, if the velocity is zero, then there is zero force applied to it. There is no magnetic force if there's not a moving charge. Okay, if the charge is not moving. All right, so here's a scenario. We're going to look at some applications of this today. Let's look at a certain field area where there's a magnetic field. And if you're wondering what I'm doing, I'm drawing a magnetic field that's going to come out of the page. So what we're seeing, that little dot in the center of the circles, is the arrow point, means the magnetic field is pointing up. And if you learn nothing else in this presentation today, learn that magnetic fields are yellow. Okay, we're going to use yellow for magnetic fields always. The reason is we're going to start putting some electric fields in here also. And that second thing you might want to learn here today is that electric fields in Shelley physics are always green. So electric fields will be green. We'll get to that later though, because we don't have an electric field right now. We only have a magnetic field. So here's an area where there's a magnetic field, and we're going to shoot a proton in here. So this proton has a velocity. It's going to enter this region where there's a defined uniform magnetic field. We'll put that in parentheses here. Okay, nice uniform magnetic field. So when this proton enters this region, something's going to start to happen to it. Up until then, it's going to move in a straight line. There's no electric fields or magnetic fields applying to it. It's only when it enters this region here. So the force applied will be a magnetic force, which is equal to, now this is a cross product we're looking at. If the velocity is parallel to this page, and as we see here, the magnetic field is coming out perpendicular to the page, then if we apply QVB sine theta, keeping in mind that vector A cross vector B equals AB sine theta in its magnitude, then we would have VB sine theta here. That's why I'm replacing the V cross B with a VB sine theta. And because the angle between them is 90 degrees, we'd have a QVB times sine 90, and sine of 90 degrees is 1. So the force applied to this positive charge, this proton I'll call it, is QVB B. And if it is a proton, that would be E, the elementary charge, which is positive 1.6 times 10 to the negative 19. So what will happen when it enters this magnetic field? This is the magnitude, but which way is the direction? Because we do have a vector product, and I kind of ignored that part. This is the magnitude of that magnetic force. But what about the direction? Well, if I turn this sideways here, help from our last lesson, the velocity is this way, in this direction. And I'm going to turn my palm so it faces the direction of the magnetic field. So I can turn my fingers up towards the magnetic field. Then the direction of the force is to the bottom of the page. So when I turn it back, direction of this force when the proton enters this magnetic field area is going to be down at the beginning there. Okay, so it's going to be moving to the right, but being forced down. It's being forced in a direction that's perpendicular to its motion. So will that force speed up the proton or slow it down or something else? If you said something else and are thinking it's going to change its direction because of centripetal acceleration, that's right. I feel like I'm a salesperson. But anyway, I'll come back to that in a moment. See, its tendency is to go to the right. Objects of motion stay in motion unless acted upon by an unbalanced force, is what we have here. So it will start to fall down and take this path instead. Right there. So there is a downward force that's starting to change its direction. What about its magnetic force at this point? Well, it's no longer moving to the right. It's now moving in this direction, kind of a diagonal here, towards the corner. Okay? So if we now look at that motion, it's now moving in this direction. And the magnetic field is still up. So now my finger's pointing towards this corner down here. Right? It is now being forced down and left. Do you see? As it moved down here, the force is now pointing towards down and left. And if we look at the force when it began entering the magnetic field and later on, they're all pointing towards a central location. So what path will it take? A circular path. It's undergoing the centripetal acceleration. So that's what happens when, to sum it up, when a moving charge enters a uniform magnetic field, what to do? It will begin to move in a circular path. It answers it. And at what speed? Changing speed? It's not going to get faster or slower. At a constant speed. Okay, there it is. When a moving charge enters a uniform magnetic field, it will begin to move in a circular path, moving at a constant speed. So I have, for us to look at, a problem there. It popped out at the bottom. Let's try it out. A proton moving at a velocity of 2 times 10 to the 4 meters per second. It's 20,000 meters per second, or 20 kilometers per second. That's not incredibly fast for a proton, but it is fast. It's actually really fast for any bit of matter. So in a particle accelerator, yeah, that's fast. It's fast. But it's in a magnetic field of strength 4 milliteslas. Now that might be slow for or small for a particle accelerator. I don't know. I don't do that kind of study. Anyhow, so we have a V of 2 times 10 to the 4 meters per second, a magnetic field of 4 times 10 to the negative 3 teslas. Determine its radius of circular motion. Now that's a key in right there. It's talking about circular motion. So if the velocity is in this direction, but the force, I'm drawing a force diagram here, is perpendicular to that direction. There it is. That's the scenario. Okay, so what do we do to find the radius? Well, if it's talking about circular motion, you might think about applying this to Newton's second law, F equals ma, where a is going to be the centripetal acceleration. So let's unpack Newton's second law. There it is. Didn't take long to unpack that. Then we have the magnetic force causing a centripetal acceleration. That's where our R comes in. How much is the magnetic force? It's QVB. The velocity and magnetic field are perpendicular to one another, so that V cross B drops out from the sine 90, and we get a QVB equals mv squared over r. So does the mass of the particle matter? Definitely. That mass won't be canceling here. The greater the mass, the greater the radius. Do you see how that ratio would have to remain the same? It's all, think of a truck making a turn. If it's going to make a turn at 30 miles per hour, if it's trying to make a tight turn, it won't make it. So the faster the car moves, the faster the truck moves, the more radius it might need, but also the more massive it is, the more radius it might need also. And that's what we got here. It's harder to swing that mass around with the greater the mass. Now we do have a velocity canceling on both sides. So we have a QB equals mv over r. And so if we solve for r, the radius, we'd have an mv divided by QB. So let's use that, the radius, to solve this problem. It's going to be what? Well, the mass we're talking about here is from a proton moving over velocity. So if you look up the mass of a proton, it's 1.67 times 10 to the negative 27 kilograms. Because everyone knows that. JK. All right, so the mass, 1.67 times 10 to the negative 27. The velocity plugged in there, 2 times 10 to the 4, divided by Q. That's going to be elementary charge, 1.6 times 10 to the negative 19. And B is our 4.0 times 10 to the negative 3 milliteslas. So 4 milliteslas. And out of that, plug it into a calculator and you'll get 0.0522, which is 5.22 centimeters. So that's not a bad distance. It's not like micrometers or nanometers. It's a very measurable concrete distance for us. It's going to make a circle about this big. Continue circling in that manner. You ever seen pictures of particles when they scatter, when they collide in a particle accelerator, also called particle collider in that case? They're going to collide, and oftentimes these energies are given off, these charged particles are given off. And you'll see the pattern that they make of motion is a swirling kind of pattern. And they may do some really funky things, but you always see a circular kind of motion because those particles are still within that magnetic field. So that brings us to our first application. Going to grab a fresh sheet of paper there. There we go. First application called a velocity selector. So a velocity selector allows us to take a sea of particles that are going in all different directions, possibly many different kinds of particles with different masses, and select only the particles going in a very specific direction, moving with a very specific velocity. So when in physics, as we continue on here, if you ever hear me saying a particle moving at this speed, blah, 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 you might be like, well, how do you know how fast it's moving if it's a proton? Well, this is how we know. We can make them or select only the particles that are moving with a particular speed using a velocity selector. And here's how it works. Start with an emitter, something that emits the particles. All right, and that emitter is probably emitting particles in many random directions. Particles might be moving at different speeds. A particle might talk about is a hydrogen atom, a single proton. You might look at helium atoms called alpha particles, or electrically charged particles, also very radioactive. It can be harmful to living cell tissue if it gets absorbed, that type of thing. But first, we need to select just a few of those particles that are only moving in a very specific direction. We want to start turning them into a sort of beam. So let's put a couple of filters here to only allow particles through that are moving in this direction. Anything moving in this direction will bounce off, or this direction will bounce off that way. Okay. So we're kind of shielding, selecting the direction. So that's called a velocity selector, not a speed selector. It can be a speed selector, but the velocity gives us a very specific direction as well. Now we allow that beam to enter a region of our velocity selector here, where we're going to specify a magnetic field. So I'm going to make a bunch of these. Got to have a strong magnetic field here, at least one that's not insignificant. Dot, dot. So it's all coming out of the page. Even though it does not look uniform, I am calling this a uniform magnetic field. And of course, what am I missing here? Have you been paying attention? Yellow. Magnetic fields are yellow. If you tend to take things too literally, magnetic fields aren't really yellow. They don't really have color. Okay, but you know, in Scholle physics, magnetic fields are yellow. Okay, so if this, let's say a proton, my proton beam, that's what we're starting with here. We're trying to select its velocity. In the last problem, I wanted to select a velocity of 20,000 meters per second. So how could I select the particles moving exactly the speed? Well, if I allow that particle to enter this zone of magnetic field, what will happen to it? Well, it's going to go this way, coming down that way. Magnetic field is up, so there's going to be a force to our left. That thing is going to start moving in a circular path and probably crash into the wall of our velocity selector. Game over. We haven't really selected anything. We can't use it yet. So when it enters this field, this magnetic field, we want to make only that speed of particle go straight. So we need to somehow force the particle to the right to balance out, I guess to your right, there we go, to the right to balance out the magnetic field force that's to the left. And we want those two forces to be equal and opposite. So what are the kind of field affects a particle, a charged particle? An electric field. So why don't we put a positive electric field, positively charged plate on this side and negatively charged plate of equal magnitude on that side. That will create an electric field from left to right. Okay, so that is an electric field over here. A. And yes, I will color B. There we go. So, what happens now? That proton will enter the magnetic field and be forced immediately to the left with a magnetic force. However, it will also be forced to the right with an electric field, an electric force. Now, if it's moving too fast, let's look at the magnitude of the magnetic force, QV cross B, And what is the magnitude of, I guess, the whole deal here? Not just magnitude, but magnitude and direction of an electric field or electric force. So electric field times, you remember? Q. All right, so the force, electric force is in the direction of electric field. But keep in mind here, the magnetic force is not always in the direction of the magnetic field. It is not in the direction of the magnetic field. However, getting back to it, let's get back on track here. The faster it moves, the greater the magnetic force. But does velocity affect the electric force? Not at all. So the electric force is constant, but the different velocities of particles are going to be affected differently by the magnetic field. So particles that are moving too fast will have a greater magnetic field to the left, and they're going to just crash into the wall. Particles that are moving too slow are going to have a lesser magnetic field, and the electric field will be greater, causing them to veer off to the right, and they're going to crash into that wall. So what we want is just the particles that are moving at a very specific velocity so that they move straight through. So we want, when we're considering Newton's second law, we want the electric field minus the electric force minus the magnetic force equal to 0. We don't want any acceleration for this very specific velocity of particle. So if that's the case, Fe equals Fb, and we plug in their expressions. QE is the electric force, and QVB is the magnetic force. Keeping in mind our velocity is always perpendicular to the magnetic field. In this case, the magnetic field's coming up, and the velocity is going down, so they're always perpendicular. Sorry, magnetic field's going up out of the page, but the velocity is going perpendicular, parallel to the page. So one is perpendicular, the other one's parallel to the page. There we go. So as you see, the Q's are going to cancel, and crazy, look at this. The velocity is going to be equal to the ratio of electric field to the magnetic field. Okay, that's it. I think it's kind of simple looking, isn't it? The velocity is the electric field over the magnetic field. Velocity of this particle. Isn't that crazy? You take a Newton per coulomb of an electric field divided by a Tesla per meter squared, Tesla meter squared, which is also called a Weber, W-E-B-E-R. Maybe it's called a Weber in some places, I don't know. But anyway, if you take those two field values and divide them out, you get a meter per second. You get a velocity out of it. I think that's pretty awesome. It's a velocity selector right there. Okay. Our second application is just an extension of that, called a mass selector, also called, make it look the same as before, aka mass spectrometer. This one you use it as a measuring instrument. This one you can use it for directing particles at a certain into a certain place. Maybe I just made that up, but I think it makes sense when you look at how it operates. So a mass selector is a velocity selector. So you start off with that velocity selector. You'll have the magnetic field and the electric field. Let me go ahead and give that color. And you do start off with your beam of particles. Okay, but in this case, what are those particles? Big old question mark. You want to select the mass. Okay, so after that particle, put the little thingy up there, that's the little blockers there. All right. You want to select the velocity of these particles first, but they could be hydrogen moving at 20,000 meters per second. It could be helium moving at the same speed. Okay, so they make it through here and into this region of space down here. But in this region, we're going to continue projecting that magnetic field. So that magnetic field doesn't go away, but the electric field does. So there's only an electric field up here, but there's a magnetic field in both areas. This is our mass selector. So once we have many different kinds of charged particles exit the velocity selector, what are they going to do? They're going to start moving in the circular motion, with circular motion. So if the velocity is down and the magnetic field is up, then there's going to be a force on a positive charge to our left. Now, if it's just the right kind of charge, if it's just the right kind of particle, say it's a hydrogen, it might end up here. It's our hydrogen. But what if it's a helium moving at the same speed? Well, heliums are more massive, so they're going to be moving. Our heliums are more massive, and if we look back at the last page, this might be an interesting thing we didn't really pick up on. We did a little bit, but if they're more massive, they're going to make a greater R, a greater radius. All right. Does mass affect this scenario here? Does mass affect the velocity selector? No, it doesn't. See, at the mass times 0 is 0. There is no effect of mass on the velocity selector. So we could have helium there, or maybe lithium coming out here. It's going to make a bigger arc. And there may be different kinds of charged particles. We could be talking about electrons and positrons, which is a positively charged electron. So you see how it would affect that radius differently. So our last little tack-on problem here is what electric field is required for our last situation. Down there at the problem, we still have a proton. Let's say a proton is moving at, again, that 2 times 10 to the 4 meters per second. We have a magnetic field of 4 milliteslas. So the big question is, what should our electric field be? So that we select just the right velocity here. So let's apply it. V equals E over B. We want 20,000 as our velocity. Electric field over 4 times 10 to the negative 3. Okay, so all we got to do is multiply that. That's 4 times 10 to the negative 3 times 2 times 10 to the negative positive 4. So 4 times 2 is 8. So our last piece here. We're going to have 8. And 10 to the negative 3 times 10 to the 4 is 10 to the 1. So that'll be 80 newtons per coulomb electric field. We now can create our velocity selector that'll help us create our mass selector. I've always been intrigued by this idea, this concept. If we could have a flow of, you know, whatever kind of materials, if we have a plasma, can we send it through a tube and have it automatically sift off the hydrogen, the helium, the lithium, maybe the iron? Could we one day take our world's landfills and start loading trash into this thing and just have it separate the materials all into their base components? There's a lot more to it than that, but it's just a thought there. Is that through overcoming some technical hurdles, can we figure out something like that? But this is also called a mass spectrometer. Generally, there's a screen that flashes or lights up that would light up in different locations to tell maybe the percentage of hydrogen or helium or different types of particles, what percentage are in that beam. So there's a lot of different uses for mass spectrometers. But that was just an introduction. I hope you got a lot out of seeing those applications. I like being able to see something very concrete instead of just talking about, oh, here's magnetic flux and this is how magnets work. But we have something we can actually do something with here. It's more of a tool. So I hope that was helpful and you've got something interesting out of it. Thanks for watching.